Welcome to Monochemistry. Today we're going to look at a slightly different way of calculating the delta H of reaction using a process called Hess's law. Now this handsome devil here is Hess, and he has the distinct honor of coming up with the law that bears his name, but he also has the distinct honor of having two S's at the end of his name, which makes it really difficult to make something possessive. I can never remember, am I supposed to put an apostrophe with no S or an apostrophe S? I can never remember. Anyway, I went with the apostrophe S, so Hess's law. Anyway, his idea was that the delta H of the reaction, the final product, the final amount of energy either released or absorbed, is actually independent of the pathway of the reaction. Now what the heck does that mean? Basically, reactions, and this is something you're going to learn about quite a bit throughout this course, reactions often aren't as simple as what is expressed in an actual typical chemical reaction. For instance, carbon plus oxygen yields carbon dioxide. There might be another step in between there that isn't expressed in that particular reaction. So they're called intermediate steps. So no matter how many intermediate steps there are in a chemical reaction, the delta H is still going to be the same for what we show in our final reaction. Let me show you. It's known as a state function. Okay, so that means that it's path independent. In other words, it doesn't matter how you get from start to finish. It just matters that you get from start to finish. So whether I follow this black line to get from start to finish, or this straight, well, somewhat straight, red line to get just from start to finish, it doesn't matter because the displacement, if you're a physics type of person, is the same. Okay, so displacement would be a state function too. It's independent of path. Sorry, not displacement. Yeah, displacement. What am I talking about? It is displacement. So independent of path. So start to finish, whether I go on a random journey, like all the way like that, the final change in energy, in this case, is going to be the same. Okay, so it's a state function. Here's an example of kind of what I mean in terms of chemistry. So what we have here is the actual reaction that we would show. So if I was to write a chemical equation on the board or in your textbook, this is the chemical reaction that I would actually write. Initial reactants, final products. Okay? And I would be able to calculate the delta H. What this shows me, what this whole picture here shows me, is that regardless of the path, whether I go here and then here, or here, here, and here, the overall delta H is going to be the same. The initial products and the initial reactants, and the final products are always going to be the same. Okay? So for example, delta H2 plus delta H3 will give me delta H1. Delta H4 plus delta H5 plus delta H6 will also give me delta H1. It doesn't matter which path I choose to go, the overall delta H will be exactly the same. Let me show you kind of something like this to show you overall what it would look like. So here we have our potential energy graph. Okay, so this is the representation of an exothermic process where I burn carbon, I combust the carbon, and I create carbon dioxide. But what if I told you that it actually occurred in 2 steps? What if I told you that? What if there were 2 steps? What if the first step involved changing this carbon, which is usually a solid at room temperature, into a gas? What if I told you that? That was the first step. And then the second step was to combine the new carbon that we just turned into a gas with the oxygen to form CO2 gas. Okay, what would that look like? So this represents the overall picture. Right? It represents the overall picture of the reaction. But does it represent what actually happens? Not necessarily, but watch what I can do with this. What color should I use here? Let's see. Green? Green. Get my Christmas colors out again. Why not? It's only, February, but that's all right. Okay, so if it's carbon turning into from a solid to a gas, that may actually require, let's see here, require a little bit of energy. Oops. Require a little bit of energy like that. Okay, so that would be carbon turning into a gas. So here would be C gas plus O2. Okay, then what's going to happen is this. Okay, notice that there were actually 2 steps in the real process, but overall, the delta H, which is the total delta H for the reaction, didn't change. Okay, the total delta H for the reaction didn't change despite the fact that I had 2 steps. So whether I'm just directly going from here to here, or whether I go through this whole rigmarole here to get to here, the delta H stays the same. And that's what Hess stated. It's logical, right? And so now what we can do is we can add reactions together, reactions that represent these steps. We can add them together and we can figure out what the total delta H should be. Right? So that in a nutshell is what Hess's law is all about. When you come to class, we will actually do some problems and you'll see what I'm talking about in terms of adding the chemical reactions together. Okay? Bring your questions to class.